Hey there, science explorers. Let's start with a simple imagination game. Picture a crowded dance floor, everyone's grooving, bumping into each other, and trying to find space to move. Now replace those dancers with gas molecules, tiny invisible ones, moving wildly in all directions, colliding constantly. Between two bumps or collisions, each molecule travels some distance. The average of all such distances is what we call the mean free path, represented by the Greek letter lambda. So in short, lambda is like the average space a molecule gets to dance freely before someone bumps into it. Pretty neat, right? Let's now see where this mysterious lambda actually comes from. Imagine each molecule as a tiny sphere of diameter d, moving through a crowd of identical spheres. As it travels, it sweeps a small imaginary cylinder through the gas, its cross-section area equals pi d squared, and it moves a distance v times t. Now, if there are n molecules per cubic meter, we call that number density, then the number of collisions in time t will be n pi d squared vt. So the mean free path, or the average distance between collisions, comes out to be lambda equals 1 divided by squared root of 2 pi d square n. That square root of 2 appears because both molecules are moving, not just one. So it's like counting both dancers moving towards each other. Okay, now what makes this mean free path change? Well, there are three main factors: the molecular size, the number of molecules per volume, and the temperature or pressure. From the formula, lambda equals 1 divided by open square root 2 times pi times d squared times n. If the molecules are bigger, meaning they have a larger diameter d, collisions happen more often and the mean free path becomes smaller. If there are more molecules in the same volume, that is, if the density or pressure increases, collisions also increase and lambda decreases again. Now, since the number density n equals p divided by k sub bt, we can rewrite the formula as lambda equals open bracket k sub b times t close bracket divided by open square root 2 times pi times d squared times p. That means, at higher temperature, the molecules move farther apart and lambda increases. But at higher pressure, they crowd together and lambda decreases. In normal air, at 1 atmosphere and 300 Kelvin, lambda is approximately 6.5 times 10 to the power of negative 8 meters, that's around 65 nanometers, or about 1000 times smaller than the width of a human hair. Pretty tiny, right? Yet, that's the average distance a molecule travels before bumping into another. Let's put this into numbers. Suppose we take air at a pressure of 1.01 times 10 to the power of 5 pascals, a temperature of 300 Kelvin, and a molecular diameter of 3 times 10 to the power of negative 10 meters. The formula is lambda equals open bracket k times t close bracket divided by open square root 2 times pi times d squared times p. Substituting the values, we get lambda equals open bracket 1.38 times 10 to the power of negative 23 multiplied by 300 close bracket divided by open square root 2 times pi times open bracket 3 times 10 to the power of negative 10 close bracket squared, multiplied by 1.01 times 10 to the power of 5 close bracket. That comes out to approximately 6.5 times 10 to the power of negative 8 meters, or 65 nanometers. So, every air molecule travels about 65 nanometers before colliding with another. You could actually fit almost 1 million such free paths across the width of a single pinhead. Isn't that mind-blowing? Even in something as ordinary as air, molecules are constantly zipping around in these microscopic journeys. Now, why do we even care about lambda? Because it's the bridge between molecular motion and the flow of energy or matter in gases. The mean free path determines how easily gases transport momentum, heat, or mass. For example, gas viscosity, its resistance to flow, depends directly on lambda. The formula says eta equals 1/3 times density times mean molecular speed times lambda. So, if molecules travel farther before colliding, they can carry momentum over longer distances, making the gas more viscous. The same applies to diffusion and thermal conductivity, all rely on lambda. So, the mean free path isn't just an abstract number, it literally controls how gases behave in the real world. Now, just like any theory, this one also comes with limits. The equation assumes that gas molecules are perfect hard spheres and that collisions are elastic. But at high pressures or very low temperatures, real molecules start to interact through attractive forces, making this assumption invalid. Also, at extremely low pressures, like in outer space, lambda becomes so large that molecules almost never collide. The gas behaves more like a vacuum. So, this formula works beautifully for moderate conditions, like normal air around us, but it starts to fail when gases behave non-ideally. Remember that square root 2 in our equation? Let's unpack that for a moment. If only one molecule were moving while all the others stayed still, we would get lambda equals 1 divided by open bracket pi times d squared times n close bracket. But in reality, all the molecules are moving randomly in every direction. This means their relative speed is higher, and the chances of a collision increase by a factor of square root 2. It's like two kids running toward each other in a hallway. They're going to bump into each other much faster than if one of them were just standing still. So, that correction factor of square root 2 simply accounts for the motion of both participants in a collision. That tiny detail, just a single number, makes the equation not only accurate but also beautifully elegant. So, let's wrap this up. The mean free path, lambda, tells us how far a molecule travels before it collides with another, a tiny, invisible journey happening trillions of times every second in every cubic centimeter of air. It depends inversely on both the size of the molecules and the number of them per unit volume, meaning smaller molecules or lower pressure means a longer mean free path. It's directly linked to real-world properties like viscosity, diffusion, and heat conduction, the quiet but constant molecular dance that keeps our atmosphere, engines, and even our breath behaving just right. So, next time you take a breath, remember, every air molecule in your lungs travels a microscopic marathon before bumping into another one. Physics doesn't get more dynamic than that. Alright, that's it for today's concept. Keep thinking, keep questioning, and I'll see you in the next fascinating journey of physics.